a three-term sequence of abelian groups a three-term sequence of abelian groups and homomorphisms. Terms uh, G prime, G, G double prime is said to be exact at G if kernel beta equal to image alpha. Right. So a three-term sequence of abelian groups and homomorphism is said to be exact at G if kernel beta equal to image alpha. Next definition is a sequence of abelian groups and homomorphisms. Abelian groups and homomorphisms indexed by integers So we can take a sequence G n plus 1 alpha n plus 1 G n alpha n G n minus 1. This is said to be exact sequence if every three term subsequence of consecutive groups is exact at its middle group is exact at its middle group. So, for example, if we consider this subsequence containing three terms, this, and this, then this subsequence is going to be exact at Gn. Similarly, next, if we consider the subsequence Gn minus 1, Gn minus 2, then it will be exact at Gn minus 1, like this. Similarly, if we take Gn plus 2, Gn plus 1, and Gn, then it will be exact at Gn plus 1. Next is definition for short exact sequence. A short exact sequence, a short exact sequence of abelian groups written as G prime alpha G beta 12.0 is a is a five-term exact sequence is a five-term exact sequence whose end groups are trivial. So these are the end groups. This and this, they are trivial. So of course, this you can extend as an exact sequence having infinitely many terms, right? You can just add 0, 0, 0, 0. This side also 0, 0, 0. So every short exact sequence is of course an exact sequence if you just add trivial groups from left and right side. Okay. So this is exact means this kernel of alpha, right, is going to be image. So here you have trivial map. This is trivial group, so everything goes to 0 here. So here so image of this map here, homomorphism, will be 0. It means that kernel of alpha will be 0. Because this is an exact sequence. It means that every three terms of sequence will be trivial. Sorry, will be exact at the middle group. So if you take this one, then it is exact here. It means kernel alpha equal to 0. That is alpha is injective. Of course, if you take this one, then it is exact at G. Then it means that kernel beta equal to image alpha. And if you consider this one, these three terms of sequence G, G double prime 0, then you will have image of beta equal to this. So here you have 0 mark. So every element of G double prime goes to 0. So kernel of this map here will be whole G double prime, and hence image of beta will be whole G double prime. Uh, So we have following observation. Observation in a short exact sequence 0 g prime g g double prime 0 beta alpha. Alpha is a monomorphism, that is injective homomorphism, and beta is an epimorphism, that is surjective homomorphism. Okay. Now, this, because alpha, since okay, so this is one observation. Second, alpha is an isomorphism. Alpha is an isomorphism from G prime to alpha G prime contained in G. And beta is an epimorphism. It means beta induces an isomorphism. Beta induces an isomorphism from so kernel beta is what? Image alpha, right? So alpha G prime to G double prime. Right? So beta induces, because beta is surjective homomorphism. So beta, so G quotiented by kernel beta is isomorphic to G double prime. But kernel beta, because this is a short exact sequence, kernel beta is nothing but image alpha. So image alpha is this. So this quotient by this is isomorphic to this. Here if we have a short exact sequence like this, then this G is called, if we have a short exact sequence like this, then G is called an extension of G prime by G double prime. So given an exact sequence, uh, Gn alpha n Gn minus 1, exact sequence, we have exact sequence, then if we put Gn prime to be, if we put Gn prime to be kernel alpha n, which is equal to image alpha n plus 1, then this 0 Gn prime Gn Gn minus 1 prime Gn minus 1 prime. So this is your this gives you a short exact sequence. This is a short exact sequence. Exact sequence. So Gn prime is what? It is kernel alpha n, right? So it is basically subgroup of Gn. So you can consider inclusion, right? So this you can consider to be inclusion in Gn. Okay, and this one you can consider to be just alpha n. Okay, so this is what? This is just kernel of alpha n minus 1 or image of alpha n, right? So image of alpha n, Gn minus 1 prime is nothing but image of alpha n. So alpha n is surjective, right? And this inclusion is of course injective, right? Uh, so we are going to have, and this you see, this. So image of this inclusion is going to be what? It is going to be kernel of alpha n, right? So image of this is nothing but kernel of alpha n. So this, it is exact here, right? It is exact here, it is exact here, right? So it will become short exact sequence. Next, a homomorphism. Next is definition. Definition. A homomorphism. Gamma from one sequence sequence gn, gn minus 1 alpha n to another sequence hn minus 1 beta n. So these two sequences will have same set of indices with the same set of the same set of indices. Is a sequence gamma n from Gn, the sequence of homomorphisms gamma n from Gn to Hn such that sequences of homomorphisms such that the following diagram is commutative. Commutative. So what is the diagram? This we have Gn plus 1 here. Gn, there is Gn minus 1. Here we have alpha n. Okay. Then here you have gamma n plus 1, gamma n minus 1, hn plus 1, hn minus 1, beta n plus 1. This is beta n. So if a homomorphism gamma from a sequence of abelian groups and homomorphisms to another sequence of abelian groups and homomorphisms with the same set of indices. So this Hn here, indices n, they are from same set, right? So for example, if here indices are on the in Z, so here also they will be in Z. So then this is a sequence of homomorphisms gamma n such that following diagram is commutative. That is, if you go this way or you go this way, it is same. Similarly, if you go this way or this way, it is same. Of course, this will be as a consequence of this, whether you go this way or you go this way, same. Now, there is a category, there is category of exact sequences with the same set of indices, and of course homomorphisms will be homomorphisms of this kind, this gamma. Homomorphisms will be sequences. So in particular, there is a category of short exact sequences. There is a category of short exact sequences, and also a category of exact sequences indexed by integers. So if we have a sequence of abelian groups and homomorphisms, Cn plus 1, Cn minus 1, and this is n plus 1, n. Okay, suppose this is, and this is G, sorry, this. So if we have a sequence of homomorphism, sequence of abelian group Cn, Cn plus 1, and so on, and homomorphisms like this, then this sequence is exact, right? Then this is a chain complex. Then this is a chain complex if image boundary n plus 1 is contained in kernel boundary n. And what we need for exactness? For exactness, we need these to be equal, right? So exactness is little bit stronger condition, right? So of course, if we have a exact sequence, that will be a chain complex, definitely. So you can say that for exactness, we have to have image boundary n plus 1. This is for every n equal to kernel boundary n. Okay. So in some way, we can say that this HNC, so we may say that HNC equal to kernel boundary n by image boundary n plus 1 is measure of non-exactness is measure of non-exactness of the sequence C at Cn, right? At Cn, if this becomes zero, right, then it means there is no non-exactness at Cn. It means at Cn sequence is exact, right? So in some way we can say that this nth homology group, right, is actually measure of non-exactness of the sequence at Cn. Next, we have following definition: a short exact sequence of chain complexes X's uh, written as this is a 5-term sequence of chain complexes and chain maps. So these alpha, beta, they are chain maps. And this is here, this is zero chain map. This also is zero chain map. Chain maps such that for all Q, there exists a short exact sequence of abelian groups. This 0 CQ, CQ prime, sorry, CQ prime, CQ, CQ double prime, 0, alpha Q, beta Q. So your let C prime C double prime 0, right? So alpha is beta. So C prime is what? It is actually chain, okay? C is also a chain complex. C double prime also is a chain complex. So for every Q, we have this short exact sequence. So here I should write maybe for all Q, following sequence of abelian groups is a short exact sequence. This is better, I think. Next definition is a homomorphism. So there we discussed about homomorphism between uh, exact sequences, right? So we discussed actually first we discussed about homomorphism between sequences. Then that gives a homomorphism between exact sequences, and hence homomorphism between short exact sequences of abelian groups. Here we are discussing homomorphism between short exact sequence of chain complexes. A homomorphism from one short exact sequence of chain complexes of chain complexes to another consists of a commutative diagram of chain maps So what will be the commutative diagram? It is C prime alpha C beta C double prime 0, then this is tau prime, this is tau, this is tau double prime, and this is C this is C bar prime, then this is C bar, this is C bar double prime, and this is alpha bar, this is beta bar 0. So if a homomorphism from one short exact sequence this to another short exact sequence this is a consists of a commutative diagram of chain maps, right? So what are those chain maps? This tau prime, tau, and this tau double prime. So these are the chain maps from here to here, here to here, and here to here, such that this diagram is commutative. So the homomorphism consists of these three chain maps, tau prime, tau, and tau double prime, such that this diagram is commutative. Now you can verify that there is a category of short exact sequences of chain complexes and homomorphisms. mark these ones.